Okay, good morning. So what I have for today, I initially thought that I will cover dual mode operation before this tutorial, but unfortunately we didn't get a chance to do so. So I'm going to walk through the dual mode operation from the lectures, and then we switch gears and talk about RMDS and the labs. Okay, so um, I just came to these are the slides. Now during the lectures we were covering OS concept 3, which was processes, and then we have some more slides to cover, but I just jumped to dual mode operation because this is a necessary um, uh, knowledge to have before I start talking about ARM DS5. Okay, sorry, ARM, before I talk about ARM Cortex A9. Okay, so what is the dual mode operation? So hardware provides at least two modes of operation. So we kind of rely on these two modes to be provided to us in the operating system. The first one is the user mode, and the second one is the kernel mode. And these are at least there should be at least two modes. As we will see in A9, it's much more than two modes. The same with Intel x86, we have more than two modes of operation. Now, any code that you run in kernel mode is considered to be kernel, and any code that you run in user mode is considered to be user code. The way, this is the basic way that hardware can support dual mode operation, is to just provide a single bit somewhere in the hardware. To set it to 0 indicates that we are in user mode, and to set it to 1 would indicate that we're at kernel mode. Now, apart from providing that one single bit, the hardware has to also provide some support, in a sense that when that bit is set to 1, you want certain operations to be permitted. And when that bit is set to 0, you don't want those operations to be permitted. Now, when you transition from one mode to another, we need the hardware to also provide some support. As we will see, we, for example, want to save PC, the program counter, where it was in the user mode when we switch to the supervised or the kernel mode. And there are some more stuff that we probably want the hardware to provide. Oh, I got a question here. When computers need hardware updates, generally an admin password is needed. Is this a switch from user to kernel mode? When computers need hardware updates, generally an admin password is needed. Is this a switch from user to kernel mode? That's a loaded question. Let me cover what I mean by user and kernel mode, and maybe I come back to this question later to see if I can answer it better. So let's sit on that question. I'll come back to it. How can dual mode operation be supported without the involvement of hardware? That's a really good question. So Let's say we have a system that only has one mode of operation, no, not dual mode. So we have a hardware that has only one mode. Can we still run an operating system without relying on this dual mode operation? The answer is yes. We don't really need two modes. The cost, however, as I mentioned in the first slide, in the first lectures, is the cost is basically performance. Now, the reason we need two modes is that we want to be able to do some stuff in kernel mode that are not allowed in the user mode. So if you only have one mode, you probably want to run your kernel at the beginning. Then the kernel can basically, like an interpreter, run the user code. So what that means is, like for instance, any interpreter, your Python or any other interpreter, they load the software, loads the instruction to be executed, and looks at the instruction to be executed, and it executes it. Now, operating system could do the same to the user code. So instead of giving full access to the user to run on the processor, the operating system could just load the software, can read the user code, and then execute it. So basically, read the first line of the code, see what it is. And if it is something that it's not supposed to do, then don't execute it. Just terminate the program. But as you can see, this is so slow. So basically, you're interpreting the code instead of running the code on the processor. So it's possible, but huge cost. So we sort of rely on hardware giving us dual mode operation for performance, so that we can, safely give access to the processor, give access to the user code to run on the processor by just setting this bit to 0, and be sure that no unauthorized instruction is going to be executed. Okay. Now, we're going to see what happens when you transition from kernel mode to user mode, and what happens when you transition from user mode to kernel mode. There are three, as I mentioned during the lectures, there are three ways that this transition is triggered, especially from user to kernel mode. So the first one is system calls, which I'm hoping to show you in the code in the lab. Let me first make sure that my lab computer is up and running. Yep, it is. Sorry for that. I just don't want it to focus on me. Okay, continuing. So the first one is system call. So this is like open, close, read, write, lseek, when you open a socket. So these are basically these are the services that operating system provides. If a user calls any of these, it means that it needs help from the operating system to, for example, open a file, or to read a file, or to write to a file, or open a socket. In that case, there's a transition from user mode to kernel mode, because we need to run kernel code, right? These are usually called traps or syscalls. So anytime a user code runs any of these, there would be a transitioning to kernel mode to take care of the kernel code. Sorry, to take care of the system call. The second is processor exception. So these are internal events caused by the user program that triggers a transitioning from user mode to kernel mode. For instance, if your code divides by 0, or if your code runs one of those illegal instructions that you're not supposed to run. For example, you don't want the user code to be able to disable interrupts. So if a user code can disable interrupts, they can kind of take control of the whole system, as we'll see. So you don't want disabling interrupts to be able to be available to the user. So if a user calls that instruction, hardware will notice and will transition to the kernel mode, and hardware tells the OS that the user used this illegal instruction. What do you want me to do? Or for instance, segmentation fault. If your code accesses a memory that it's not supposed to access, or a page fault, as we will see what page fault is, but it's kind of like another very similar to segmentation fault. So we say these are internal or synchronous because they're caused by the software. So it's something from within the software. The third category is interrupts. So interrupts are external and asynchronous events. So your software is running and then timer interrupt goes off, or your software is running and somebody types on the keyboard, or your software is running and a packet comes from the NIC. So all of these, they would interrupt the processor execution, and these are external. So your software is not causing it. Some external event happened, and hardware immediately interrupts the running program and transitions mode to kernel and tells the kernel that this event has happened, like timer went off, or a packet came, or the IO file that you wanted me to, file that you wanted me to bring to memory is ready. So I have the file for you. The bytes are ready sitting in the memory. So these are external events. These are interrupts. Now, we want this transitioning from kernel to user mode to happen in a safe manner. So the whole purpose of having two modes was because we wanted to protect to protect kernel and users from each other. I mean, you can protect kernel from users, let's put it that way. So we wanted to give more admin role to the kernel code and limit the access of users. Now, when we're transitioning between these two modes, we have to be super careful how we do this transitioning so that the purpose of the whole having two modes is not jeopardized. So the first thing that we have to do, the first requirement, is that we need limited entry points to kernel. So when we transition between these two modes, the hardware is going to go and run kernel code. So transitioning from user to kernel, now we're going to run kernel code. We don't want to jump to some arbitrary code in kernel. If that was possible, then it's a security risk, because let's say, for example, the user says, open this file for me. And if it is possible to jump somewhere in the open file, the user could open maybe some file that it's not supposed to open, right? By just, making sure that it jumps to the right position and the data is in the right place so that it gets what it wants. Or it could, impose some jumps to some kernel code that will destroy the kernel. So we don't want this to happen. So we have to have limited entry points to kernel. So we have to be sure when the transitioning happens, we start from a well-defined position in the kernel code, and everything has been thought of. We don't jump an arbitrary point. The second one is that we need atomic change to processor state. What do I mean by that? So your processor right now, let's say it's running a user code. So the PC is pointing to user code. The registers contain whatever that user code was doing. Your stack pointer is pointing to user stack, all of that. Now, all of a sudden, you want to start running kernel code. So PC should point to kernel code. Registers should now start getting the values in kernel code, and so on. And the stack should also point to, as we will see, a kernel stack. So there is this transitioning from these two modes. It's not just setting that bit to 0 and 1. We also want to change the state of the processor, which is the PC, the stack pointer, all the registers, to change from what they were holding to now hold kernel values. And we want this to be atomic. So we'll see how this is implemented, but in a sense, we want this to happen in an atomic way. So when we change a state, we want PC to change. So PC was pointing to user code. Mode changes, we want PC to now point to the entry point of kernel. We want the stack pointer that was pointing to kernel, to user stack, to change to kernel stack, as we will see. And we want all of this to happen atomically. And the third requirement is a transparent and restartable execution. Now, once we're done with whatever kernel is supposed to do, if it was a system call, let's say we wanted to open a file, if it was setting up a socket, whatever that was, if it was an interrupt and we wanted to handle the interrupt and we're done with that, then when we want to come back, we want to restore the state of the user process, so that from the perspective of user process, nothing happened. So whenever you're coding right now, right, you're not thinking about, oh, what happens if a timer interrupt goes off in my code? Because it's transparent to you. Your code doesn't even get noticed. So that's what we want the operating system to be able to implement. That's a requirement for this safe mode transfer. Now, let's start with the first one, secure entry point. This is called interrupt vector table. So this is a table set up by the operating system to point to the code that has to be executed if any of those three triggers happen. Now, in an x86, so this is a table that operating system sets up. In x86, the first 32 elements are reserved for different type of processor exceptions. Like if you divide by 0, one of the entry points is for that. If segmentation fault happens, one of the entry points is for that. If page fault happens, one of the entry points is for that. So the first 32 entry points in x86 are designated to processor exceptions. From 32, the 33rd element until the 256th element, these are reserved for different types of interrupts, like the timer interrupt, let's say, IO interrupt, and so on and so forth. So you might have multiple timer interrupts, as we have in our DE1 boards. Now, this is a convention in x86, the 64th element, the vector number 64th, which corresponds to 65th element, is reserved for system calls. So all system calls have the same entry point. So basically, when the software calls system call, we're going to go and execute that function. That function is going to look at the input and see what system call is being requested, and then from there jumps to that corresponding system call. So basically all the system calls that you have, open, read, socket, all of them, initially we start with the same code, and there we look at the exact system call that was requested, and then we jump to what was requested. Now, what like a few slides ago, I talked about user stack and then kernel stack. I said SP was pointing to user stack, and now SP is pointing to kernel stack. You might actually ask, what is a kernel stack? And why do we need a kernel stack? So one of the things that I said about safe mode transfer was this transparent transfer of mode. So to do that, we need to save the user process state. So we need to save it. Now, where should we save, for example, the PC of the user? Where should we, okay, somebody's asking, where is the interrupt vector table stored? So different hardware have different conventions. So they tell the operating system that you have to you have to set up the table in this address. Now, I will show you in a bit how it's done in ARM Cortex A9. So I will show you in the code how this is done. So just hold on to that question. I'll come back to it. Okay, so where should we save the user state? Can we use the user stack to save it? So can we just use the user stack and save everything there? The answer is no. It's unsafe to use the user stack to save user state, especially if you have a multi-threaded environment. The reason is, first of all, reliability. So if we are to use the SP, what happens if the SP is not set properly, is pointing to an invalid address? Like it, you know, and then we start saving stuff on the SP, that would be bad, right? So we should not rely on the user memory to do anything. The second is, what if, let's say, SP was actually pointing to the correct memory location and everything was set up, and we start saving the state of the user thread on the user stack. But let's say that this process that we just interrupted one of its threads has multiple threads, and we're going to at some point go to another thread, and that other thread has access to these threads a stack. As I mentioned, all threads have access to each other's stacks. So now this thread can mess up the stack, and next time the operating system wants to use the stack, now there are garbage stored on the stack. So we, as an operating system, we're supposed to save the state and come back to it whenever we wanted, but now it's all garbage because we saved it on user stack. So we're not going to trust the user. So as a result, we are going to have something that is called kernel interrupt stack. So we're going to allocate kernel stack for basically kernel code. So kernel code has to have kernel stack inside kernel memory. And we're not going to use user stacks for anything because of what I just said is bad. Now, some operating systems take a step further, And instead of having one kernel interrupt stack to use for all kernel code, they designate separate stacks, separate kernel stacks per user thread. So they say, thread 1, I'm going to designate a kernel stack for you. So anytime I want, anytime you call system call, I'm going to use your kernel stack. Every time an interrupt happens while I'm running your code, I'm going to use your kernel stack that I designated to you. So basically, each user thread gets its designated kernel stack inside the kernel memory. And this is some operating system, as I said, have only one big kernel stack for all threads, and some operating system, most of them, and the one that you're going to implement, has a separate kernel stack per user thread. And this kernel stack, as I said, is used every time that particular user thread gets interrupted or calls a system call or an exception happens. So anytime we switch from user mode to kernel mode while running thread 1, we will use thread 1's designated kernel stack. Okay, so this is just an example before I jump to the code in the remaining 20 minutes. So as I said, this is the 2-stack model right now. Assume that I have a user stack in user memory. So this for just so this is user memory. This is in user memory. This is in kernel memory. So we keep the kernel stack in kernel memory. So as the user code is running, we just use the user stack, like main, then let's say process 1, and then procedure 1 and procedure 2. So these are function calls. As we saw in the lecture, we're going to use the stack for function calls. Now let's say at this point, this function called a system call, like open, like we were 3 levels in, and then we called open. So what happens at this point is that there is going to be a switch from user mode to kernel mode. So now we're going to go to kernel mode. So we're going to handle the system call now. So we basically pause here from what we were doing with the user code, and we're going to go to kernel code. And the first thing we're going to do is to save the state of CPU on the kernel stack, as I mentioned. So because we want to have this transparent switching, so we're going to save the state of CPU on the kernel stack. And then, well, now we have to handle the system call. We probably need to use this. This might also have function calls, whatnot. So we're going to use the kernel stack now for this one. For example, let's say this is the system call handler. And then let's say the system call handler is going to call, let's say you wanted to open a file. So now the system call handler is going to tell the SSD driver to bring me these bytes, right? So we're going to call the function like IO driver as a function call. So it's going to use this as well. Now, let's say IO driver comes back and it's done. So we just remove the frame for IO driver. Let's say the system call handler is now done. It copies the file into the user memory. So it's done. So we grab that. Now we're ready to context switch back to, not context switch, sorry, to switch back to the user, right? So at this point, the user code is ready to be executed. Now, because we haven't yet gone back to it, we still store the CPU state here. The moment we want to go back to running the user process, we will just put these guys into CPU registers. And we're good to go because we saved all the registers. Now we can just load them, and then we can just go ahead and execute the user code. Okay, so that's where I'm going to pause here on the slides, and now we're going to go and see everything that I mentioned in the code and in the ARM processor. Okay, before going to that, let me answer some of the questions that you guys have asked. So I'm going to go back to the first question that somebody asked. When computers need hardware updates, generally an admin password is needed. Is that a switch from user to kernel mode? Not necessarily. So you have different kind of admins, like you have the root, you have, you know, different users, right? Now, the admin of the root, let's per se, of the Unix is another user with more what to say, with more access to certain things, like update certain things. But the kernel switch that we are talking here, we're talking about running the kernel code. So these are two different things. For example, let's say, you know, you as a user of the lab computers, your access is limited. Maybe you cannot install a new software, and an admin should come and install the new software. That's different. Those are access controls to the system. You might not have access to certain files, for example. But the one that we're talking about here is access to executing the instructions. So we're talking about kernel code versus user code. So we're not talking about different users of the system. We're talking about any user code and kernel code. I hope I answered that question. It was a little bit loaded. Okay, so where is the interrupt vector table stored? This is going to be the first thing I will show you in the code. So is the kernel stack here the same as kernel level stack that was explained in last lecture? So yes, these kernel stacks are also kernel level stacks. There might be other kernel level stacks for kernel threads themselves, but these are also kernel level stacks. So, but these are not the only kernel level stacks. We will talk about this when we talk about multi-threaded kernels. So I will come back to it. But yes, these guys are also kernel level stacks. There are other kernel stacks that we'll talk about, but these are also kernel stacks. So for each thread, kernel maintains its own kernel stack and its own TCB. Yes, that's correct. So if I were to just show you, now that two people have asked this, where is my Chrome? So it's here, next topic, multi-threaded kernels. Let me just open it and show it to you. Just the, oh, yeah, download, okay. So this is basically how it looks. So for each, so here I have so this is the user level process. So let's say process 1 and process 2, and let's say each one of these have 2 threads. Now each thread has its own stack. So these are user level stacks, right? Now for each one of these threads, the operating system, now this is kernel. So this one is kernel memory. This one is user memory. So inside kernel, we're going to have one stack for each thread and one TCB for each thread, as you can see. So this stack is for this thread B of process 1. Now, these are not the only stacks that we have. As you can see, now kernel might have its own threads, right? And each one of them will have its own stack as well. So now all of these guys are kernel stacks, and these guys are user stacks. I hope that this is explaining what I mean by, kernel stacks from the previous lecture, the previous question that was asked. Okay, so we answered that. What happens if there is a file pointer being returned due to the file system? That's a good question. So going back to the slides, here, as you can see, I removed the system call frame from the stack, right? So once you return from the system call, you might actually change some stuff here. Maybe put the return address into this process called system call and was expecting a return. So the return goes and being written here. Let's say if the process had like int value equals I don't know, some system call, then once the system call is executed, we set the value and we're ready to go back to that process. So we make some changes regarding to that system call in the user memory. For example, if the user opened the file, so we want to bring the data from that file to user memory. So we're changing the user memory. So the operating system is going to copy the file to the user memory and set the pointers. So that's done as well. Okay. Now let me, without further ado, go and talk about the lab. Okay, so share screen. Okay. So this is your code. This is lab 1. Hopefully I can run it. Let's oh, it's not actually. So these are from delete. Yes. And delete. Oops. And so. Okay, so we're gonna open the project. I have it here. So this is the RTX. You're gonna open it. Finish. Okay, so this is our project. We're gonna build it. Good. Now we're gonna click on this RTX launch to launch the project. Everything looks fine. So we click on debug. Okay, let's see what happens next. There. What you see here is where the operating, this is the first code that is going to be executed. Now we're interrupted at the entry point of operating system. And read these. This is reset address, undefined address, SVC address, PABT address, DABT. So this is pointer abrupt. This is data abrupt address. Okay, so what are we doing? Let's look at, this is where we are setting the interrupt vector table. Somebody asked, where are we setting the interrupt table vector? I told you that this interrupt table vector is set by the operating system. So we're going to tell hardware that if a reset exception happens, go and execute this reset address code. If an undefined exception happens, go and execute this guy. If a system call happens, this SVC address, we're saying if a system call happens, go and execute this code. So if you click on this code, you will, this fortunately I cannot click on it because I'm executing it. But anyhow, this SVC address is the address of so these are all defined here, right? If I click on SVC, I can't click on it. God damn it. But anyhow, so this is a convention in ARM that, for example, as I was telling you, for instance, for x86, the first 32 entries are for exceptions, and then entry 65 is for system calls. In ARM, the third entry is for system calls. So if you go and read the ARM document, it says the 8th byte of the interrupt table should point to system call handler. So because this is a 32-bit system, each one of these two have 4 bytes. So that's 8 of them. So this is the last of the 8. So this will point to the system call handler. So this is 0 to 7, the first 2, and then the 8th one is going to be pointing to the system call handler. And to just look at this code, what does it do? LDR PC this guy. So it says save this address to where PC is pointing to. So now I can open the registers, go to core, look at my PC. So PC is pointing to this address. So I'm saving this reset address to PC. Now, if I go to, for example, my memory, and I can put, I can copy this register. Sorry, I'm in Mac, and I'm gonna guess that this is copying. Okay, memory, Control V. Oh yeah, okay. So this is right now what is stored in that address. If we execute this line, oh, did I jump? What did I do? Sorry, guys. Oh, I stepped in the source code. I wanted to step like in the assembly. So let me do it again. Okay, I actually better jump. I have only four more minutes. So anyhow, so if you execute this, you're gonna write the address of reset in where PC is pointing. So basically, this is where you're setting up your interrupt table. Now, the most important thing that I wanted to talk today about is on this document. Let me switch. So this document that is pointed to in our lab manual should be your friend. So this is basically introduction to the ARM processor using Ultra toolchain. So this document, you should really read it and be familiar with it. The first portion that I wanted to talk that is related to the slides that we saw. I talked to you about this single bit that you set for user to kernel mode. Now, in ARM, you have more than one mode of operation. In fact, you have, let's see how many modes you have. So this is section 9 of the document. And as you can see, you have 1, 2, 3, 4, 5, 6, 7. You have 7 modes of operation in ARM Cortex A9. So in the lectures, I said at least 2. But then here we have 7 modes of operation in A9. The ones that we're using for the labs are the user mode and the supervised mode, the supervisor mode. So we're saying that this is the user mode and this is the kernel mode. So these two are the ones that we're using. And as you can see here, this is the SVC, it's called SVC mode. And then there is the user mode. There are other modes, but we're not using them in your labs. Now, going back to the slide I started. So how do we know which mode we are at? We look at this status register. So this status register, which is called CPSR. Let me highlight it. This guy tells us what mode of operation we are at. So by looking at this guy, we can, looking at these bits 0 to 4, we can get the processor mode of operation. So if you had only 2 modes, you only needed 1 bit, 0 or 1. Now we have 7 modes, so we need at least 3 bits, right, to represent. Now these guys have allocated 5 bits, which is more than enough. We only need 3 bits of it. But the reason that there are 5 bits is because the numbers for modes are not just 0, 1, 2, 3, 4, 5, 6, 7. So they use different numbers for different modes. That's why they designated 5 bits to this to user mode. There are other stuff here in the CPSR register, but you don't need to worry about them. For example, we're not going to use the thumb operations, so this we don't use. The interrupt bit disable is here. So if you want to disable interrupts, you're going to use these bits. And these are the condition flags. So condition flags, for example, if you had an operation and the result of that operation was 0, then this 0 bit will be set 0. If you had a condition instruction and it was taken or not taken, this condition bit changes accordingly. Somebody has asked what CPSR stands for. That I really don't know. I don't know what it stands for. It might actually be in this document. Now, one last thing before I end this tutorial. I know I'm over time, sorry. One thing before I end this tutorial, I want to talk about how we save. As I said, one of the things that we need to do is we need to have safe, we have to have atomic mode transfer. So it's not just setting this bit, we also need to save the PC and a stack pointer of the user code. I want to show you how that happens in ARM, and then I end the lecture. So for this, I'm going to come to this slide. This might actually look a little bit scary at the beginning, but let's look at this. So these are the, So the first column here, I'm looking at this column here. These are the registers that we just saw. So from R0 to R15, and then CPSR. So these are the set of registers that we have. Now, when context switch happens, when the mode transfers, so if the mode transfers, meaning that we go from user mode, we go to kernel mode. The moment this happens, what happens? So nothing happens to R0 to R14, to R12, sorry. These, they don't get touched, nothing happens. Now, the PC register is going to point to wherever it has to be pointing to according to the interrupt vector table. So if we're changing mode because of a system call, then PC is pointing now to the system call handler. If it is an interrupt, then PC is pointing to the interrupt handler. But what happens to the old PC? What happens to the PC that we had before when we were running the user? That PC gets stored in R14 SVC. This is a new register. This is not R14. This is R14 SVC. So these blue boxes here, these are extra registers that hardware has on top of these registers in this box. So on all the registers in this box we have, and then plus all the blue boxes, these are new registers. So hardware takes a copy of old PC and puts it in this register. It also copies this old CPSR here in this blue register. So CPSR gets copied here. And I also mentioned about a stack pointer. It copies the stack pointer in here. So it makes a copy of the stack pointer. Oh, sorry. No, it doesn't. It does not copy. Sorry. So it doesn't change the stack pointer. The R13 stays what it was, but R13 SVC will point to kernel stack. So this is something that the operating system has to set before. So whenever you want to go and run the user code, you should set this R13 SVC to point to the kernel stack of this thread. so that whenever we context switch to kernel mode, this R13 SVC is already pointing to the kernel stack, so that we can use the kernel stack going forward. If you want to access the old SP in ARM, you do this. So by doing this guy here, you're saying I want the SP of user. I don't. If you just use SP, you're going to use this R13 SVC. So this guy. So if you are in the SVC mode, if you just access SP, you're basically accessing R13 SVC. If you want the stack pointer of the user, you have to use this guy. Now let me just show this in the code as well, and then end this session. Again, apologies for this being a lot longer than it was supposed to be. So let's go back to the code. Here is an example of that. Let's go to kernel hal.c. We're going to talk about these files in details when we go to lab 2, but I just want to show you. So this is basically the SVC handler that I showed you, right? This is here. We were saying this is where we're setting up the interrupt table. We're saying put this SVC address in this, and SVC address is SVC handler, and SVC handler is defined here. So when system call happens, we're going to come and run this function. So the PC will point to this SVC. Now, look at this here. This is what I was talking. So if you want to get the SP of user, this is how you access it, with this symbol here. This means that I want. Look at this one. This one doesn't have anything. This one is just SP. So this SP is basically it's R13 SVC. This SP, because I have this symbol here, is basically the actual R13. I repeat again, this guy, because now we are in SVC mode, because we're running this SVC handler, the mode has changed. In SVC mode, SP, if I just use SP, is basically R13 SVC. And SP like this is the actual R13, one of those black boxes. So this one is a blue box. This one is the black box. So here we are. So this is the last thing I wanted to show you. Again, we'll try our best to use this tutorial to walk you through the kernel code. But I just wanted to mention how the A9 handles mode transfers. And to just recap, I showed you the interrupt table in our code, how it's set up. The first thing that runs sets up the interrupt table. The second thing I showed you was where we save the mode of operation, which is basically in the CPSR, in the status bits. We keep track of the mode. And the last thing is how we atomically change a state. So when we atomically change mode of operation. When mode of operation changes, not only the state bits here change, we also copy PC, we also copy CPSR, and we also switch to a new stack. So these are the hardware supports by A9. Okay, I'm going to pause here. There are a bunch of questions. So what does SPSR stand for? I think I said I don't know. Somebody is asking for the material we have talked about so far in the lectures. Where can we find practice questions? Apart from the final exams posted. Apart from those, I would say read the book. So in the book, you have exercises, and also there are these tests inside the textbook. So you're reading a chapter. At the end, there's like a question answer about that chapter. So these are really, really important. So look at the book. Look at these kind of, I think it's called test. Let me look it up. So yeah, every here and there in the book, there are these, if I can find one. Yeah, anyhow, yeah, here, like, I don't know how to show it, but things like this in the textbook, you have example answer. So there are many of these in the book, and then there are, you know, questions at the end of each chapter. So these are another sources you can use to prepare. Mode transfer is not a context switch. Is this correct? Mode transfer is the beginning of context switch. So mode transfer is just mode switch. You just switch mode. Now you could decide to context switch. Let's say, for example, let's say timer interrupt goes off. So that's an interrupt. Because of that, a mode transfer happens first. So you're going to go from user mode to kernel mode. Now, in kernel mode, you might decide to context switch. You might decide that, OK, I'm done with running this thread. I want to run another thread. So the time is up for this thread, and I want to start another thread. So at this point, you start context switching. So context switching means you go from one user process or one user thread to another one. Mode transfer means from the user mode, you go to kernel mode. So usually, mode transfer is the beginning of context switch. So for any context switch, you need a mode transfer. So you're going to transfer to kernel, do the context switching, meaning that you switch from the context of thread 1 to context of thread 2, or from context of process 1 to context of process 2. And then you have another mode switch from kernel this time to user to complete the cycle. And then context switch happens. So yes, mode transfer is not a context switch. It's a requirement for context switch. OK. Thank you for everybody who attended this, and thank you for those of you who are going to watch this. Talk to you next week. Take care. Be safe. Bye-bye.